Hey guys, welcome to chapter 7. We're going to cover section A today and talk about chemical reactions. Feel free to follow along in the book with me. All right, so just a little review. Remember, we've talked about physical and chemical changes before. A physical change just alters the form of a substance or the state of a substance, but a chemical change comes up with a completely different substance. It's when two or more elements chemically combine or break apart to form something totally different. Okay. We can also refer to those chemical changes as chemical reactions because every single chemical reaction is a chemical change. Okay. And when you have a chemical reaction, what happens is you start with one substance and you wind up with a completely different substance. Okay. Now, how do you know? All right, so there's lots of different things we look for to determine whether a chemical reaction has taken place. If I just pour salt into water, I'm not going to see these things happening. I still have H2O and NaCl, sodium chloride. Okay. But these are some specific pieces of evidence that you look for. The formation of bubbles, okay, that tells us the gas is being produced. We definitely see that when we mix baking soda and vinegar. The reason it foams is because gas is being produced. Anytime there's a color change, sometimes you put two clear liquids together and you see they change color. So like this one right here, okay? Putting in a liquid into a clear liquid, and all of a sudden there's red. Sometimes things turn black. Maybe that's just because it's burning. But burning itself is another evidence of a chemical reaction. Anytime something's burning, that is a chemical reaction. The formation of a precipitate is another sign of a chemical reaction. That's what most of these pictures are. A precipitate is when a solid forms from two liquids. Okay, so you can kind of see this powder settling at the bottom of those test tubes. If you mix certain liquids, they actually will form this solid precipitate. Obvious sign of a chemical reaction there. I wish I had an example to show you guys, but I don't. I don't have the right chemicals for that. A temperature change is a pretty obvious example or a piece of evidence for a reaction. In all reactions, energy is either released, like it's sent out as heat, or it's absorbed. Okay. So think about the disposable ice packs that are in all the like sports first aid kits. When you pop that, what you're doing is you're introducing two chemicals together that are absorbing all kinds of energy, and so it feels very cold. You can also have the reverse hand warmers. Okay, when you open a hand warmer, the oxygen in the air reacts with whatever's in that packet, and it releases heat, and we feel that as it releases energy, and we feel that as heat. So any kind of temperature change is an indication that a chemical reaction is occurring. And again, with that energy release, sometimes we see that as light. When you snap open a glow stick, those chemicals combine and they start to glow and they emit light, and that's just energy being released. Okay, so all of those are signs of chemical reactions. You can also see something that's referred to as composition change. When you bake bread, okay, you start with a batter, and when you bake it's just different. The composition of it has changed. This is different than like melting or something freezing, because I don't know. I don't know how to explain really why it's different, but it's almost like you're winding up with a totally different substance, okay? Which you are, because it's a chemical reaction. All right. So we write these equations. They're not math equations, they're chemical equations to show the reactions happening, okay? The reactants are the things on this side, on the left side of the arrow. That's what we start with. That's our raw materials, okay? Then the arrow indicates a change is happening. This is our starting point, then something happens, and then this is what we wind up with. And those are known as products. Totally new substances, new materials, okay? We've already talked about the subscripts of these formulas, okay? But now we've got these larger numbers in front of some of these compounds here. Those are called coefficients. And what that means is I actually have two compounds, 2 molecules of oxygen. I only have 1 compound of this CH4. I have 1 molecule of carbon dioxide, and then I have 2 molecules of water. We're going to talk about why we need those coefficients, but basically it's to balance the equation, okay? The last vocab for these equations is the word mole. Mole, mole, mole. It is a ginormous number, okay? So since we're dealing with atoms, there are so many atoms. The book gives us this crazy amount here. It says 1 nanogram, which is a billionth of a gram, so a tiny amount of hydrogen contains almost 600 trillion atoms of hydrogen. So we're dealing with these really big numbers, right? So scientists came up with this constant, this number. It's known as Avogadro's number, Avogadro's constant. It is 6.02 times 10 to the 23rd power. That's the amount of atoms you have in 1 mole. So if I have 1 mole of hydrogen, I have that many pieces of hydrogen. If I have 1 mole of oxygen, I have that many pieces of oxygen, okay? So the atomic weight on our periodic table is actually the mass of 1 mole of that element. So we know that oxygen is right around 16 atomic mass units. That means 1 mole of oxygen weighs that. It's sometimes also referred to as the molar mass, okay? And what that means is that you have, and then 21 zeros after it. That's how many actual atoms of that element you have. Huge number, okay? You should just know the definition of mole. All right, so now let's talk about balancing equations. The law of conservation of mass tells us that we need the same amount of what we started with and what we wound up with, okay? And so here's the same reaction as the previous page, but it's not balanced. And so if we actually count out the number of elements in their ratio, we see that on this side I have 4 hydrogen atoms. I only have 2 on that side. I have 2 oxygen atoms on the reactants, and I wound up with 3, okay? So it looks like I lost hydrogen and I gained oxygen. That can't happen. So we have to use these coefficients to change the number of molecules so that the number of atoms in the reactants equals the number of atoms in the products, okay? So that's why there was a 2 in front of each of these compounds, okay? I'm going to show you on the next slide what that does and what that means, okay? But understand that we can change the coefficient, but we can never change the subscripts, okay? If I needed, if I started with water and I just needed 1 more oxygen, I can't just stick that there because now I don't have water anymore, okay? I can only deal with the coefficients, and I can't stick something in the middle. So if I have carbon dioxide and I needed another carbon, I can't just stick a subscript there, and I can't stick a coefficient in the middle, okay? It can only go at the beginning, and it applies to the entire molecule, okay? So how many atoms do we have in each of these? It kind of works like distribution, okay? So this 3 applies to those hydrogens and those oxygens. What it means is I have 3 water molecules, okay? So I would have 6 hydrogen and I would have 3 oxygen in that situation, okay? I don't have a coefficient there, which means I only have 1 of them. So I have 2 iron and 3 oxygen. That's pretty easy. But if I do put a coefficient in front of it, remember it applies to each of these. That means I have 4 of those molecules now. And so I would have 8 iron and I would have 12 oxygen, okay? It applies to each element. Each capital letter is a new element, okay? So I would have 4 hydrogen, I would have 2 sulfur, and I would have 8 oxygen. Now we can get into these extra subscripts, okay, that get a little more complicated. I'm just going to show this to you right now, but I'm not going to test you on this. This only applies to that portion of the formula, okay? Remember, we've got those polyatomic ions that kind of act as their own unit. So this would mean that I have 3 barium. I would have 2, what would that be? Phosphorus. And I would have 8 oxygen. Okay, the 2 does not apply to everything. If the 2 was out here, it would apply to everything. Okay, so that's the only time I can, but I'm not adding those subscripts to balance the equation. That's the formula. Okay, that's what that subscript outside of the parentheses means. Okay, I don't add that myself. I can only add coefficients. All right, so the way you balance equations is you literally count how many atoms of each element you have on each side. So on this side, I have 1 magnesium and I have 2 oxygen. On the product side, I have 1 magnesium, but I only have 1 oxygen, okay? So that's unbalanced. So I need to stick a 2 in front of there to increase my oxygen to 2, but it also applies to the magnesium. So now this is up to 2, which means I have to go to the other side and put a 2 in front of that magnesium to make that a 2, okay? So now that's a balanced equation, okay? I didn't change any subscripts, just coefficients. All right, so let's look at the next one. You're kind of recommended to deal with oxygen and hydrogen last because they're so common. But when you've got these 3s and 2s, you want to kind of look for a common denominator. So I've got 2 aluminum on this side. I've got 1 on this side. I've got 3 oxygen on this side, and I've got 2 on that side. So I'm going to go ahead and just stick a 3 here and a 2 here because I need that common denominator of 6, okay? So that's going to give me 6 oxygen over here and 6 oxygen over here. But since I put a 2 in front of this compound, I'm now up to 4 aluminum. So I simply come over here and put a 4 there, and now I have a balanced equation, okay? Sometimes the equation is balanced, and we might not even realize it, okay? Now, I've got hydrogen in 2 different spots here, so I have to make sure I count all of them. So I have 2 hydrogen, I have 1 Cl, I have 1 sodium, and I have 1 oxygen. Go over to the other side. I have 2 hydrogen, I have 1 Cl, I have 1 sodium, and I have 1 oxygen, which means this is a balanced equation. I don't need to add any coefficients at all. Okay, one more, okay? This is photosynthesis, and photosynthesis, as it's written right here, is not a balanced equation. This one's a little trickier. So I am going to start with the carbon this time. I'm going to leave the oxygen and the hydrogen till last, but let's go ahead and total up what I've got. So on this side, I have 6 carbon, I have 12 hydrogen, and I have 8 oxygen because I have it in 2 different locations. Over on this side, I only have 1 carbon, I only have 2 hydrogens, and I have 3 oxygens. That one's not going to be very fun, okay? I'm going to deal with the carbons first, so I'm going to just stick a 6 right here, okay? Which brings my carbons up to balance, but it changed my oxygens, okay? So now this 6 gives me 12 plus 1. I'm up to 13 oxygens. That's weird, okay? Let's see, what should I do next? I'm going to deal with my hydrogens now. I've got 12 on this side, only got 2 on that side. So I'm going to put a 6 in front of that to give me 12 on that side now. But you can see that that's going to increase my number of oxygen, okay? So now I'm up to 18 oxygen, okay? Again, because I have 12 there, plus 6 is 18, okay? So I come back to the reactant side, and I have 8, so I've got 6 here and only 2 here. If I put a 6 there, that gives me 12 plus 6, that gives me 18. Magically, my reaction is now balanced. It gets easier with practice, like anything else. I know it's confusing now. We'll do more of these in class, and I'll share a website with you that will help as well. Okay? That's all. See you guys.